Alright, so now let's go ahead and actually look at a problem where we solve a standard minimum. We can take advantage of the fundamental theorem of duality, and the fundamental theorem says that a standard minimum problem has a solution if and only if its dual problem has a solution. So if we think about the, any standard minimum problem, we can set up the dual problem. If we can find a solution for that dual, then that means the standard minimum, the original problem, has to have a solution. What's even nicer is that the standard minimum and the dual have to have the same optimal value. So this last sentence is the key thing. So the standard minimum and its dual have the same optimal value. So that means that if we find a dual solution, remember this is a maximum problem, then our objective function, say it has a maximum at 3, then the standard minimum problem would have a minimum of 3. Okay, so they're going to have the same value right there. And so that's really nice. So let's go ahead and see how we can actually solve a standard minimum problem here. So we have a standard minimum problem. The first thing we need to do is come up with the dual problem. So we're going to need to write the original augmented matrix, and then we will transpose it to find the dual. So let's see, I'll call this A, and so this would be a 7, a 12, let's see, a 6 and 18, -5 and 4, 1 and 6, and then we have 45 and 86. Along the bottom row, we need to put the objective function, z equals, so our coefficients will be 40, 60, 50, 35, and we'll have a 1 in the last column, because we have one z, okay? Alright, so here's our original augmented matrix, and now we need to transpose it, and so that will give us the dual problem. So now our transpose, if the original matrix was a 3 by 3 by 5, this was 3 by 5, then the new one is going to be a 5 by 3, because the rows and the columns are going to switch. So let's see, A transpose, I'm going to take the first row, right, the first row, and that will become the first column for the transpose. So we'll have 7, 6, -5, 1, and 45. Now we do the same thing with the second row. So row 2 becomes column 2. So we have 12, 18, 4, 6, 86. And last but not least, row 3 becomes column 3. So we have 40, 60, 50, 35, and 1. So here's our transpose matrix. The objective function now is given by 45 and 86, and we now have 4 constraints instead of 2 constraints like we did before. So now let's go ahead and write our dual problem. So the dual problem says the following. We want to maximize, and now we're not going to use z, we have to use a different letter. So let's maximize w equal to, and our variables can't be x's, so let's let them be y values. So this will be y1, y2, and our objective is going to be w. So let's maximize w equals 45y1 plus 86y2, and this needs to be subject to the following constraints. So subject to. So now we have the first constraint, and that is row 1. So we have 7y1 plus 12y2 must be less than or equal to 40. Let's get the second one. We have 6y1 plus 18y2 is less than or equal to 60. -5y1 plus 4y2 is less than or equal to 50. And y1 plus 6y2 is less than or equal to 35. Alright, great. Oh, and we can't forget, y1 and y2, of course, must be greater than or equal to 0. So now, if we look at the dual problem, this is a maximum problem. We have a standard maximum, and so we can go ahead and use the simplex method. So let's set up the initial tableau, and then we will go from there. So let's set up our initial tableau right here, and let's see. I'll go ahead and set it up on the side right here. So we have y1 and y2 are the variables. We have to have several slack variables, and I'm going to run out of room because we need to have 4 slack variables. So I'll go ahead and set this up down here. So we have y1, y2. Now our slack variables are going to be 4, there are 4 of them because we have 4 constraints. But think back to the original problem. Originally we had 4 variables. And so these slack variables are actually representing our original variables, x1, x2, x3, and x4. So we'll have x1, x2, x3, x4, and of course we'll have w instead of z, and then our constants. So if we write our maximization dual problem into our tableau, we should have the following: 7, 6, -5, 1, 12, 18, 4, 6, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and, not yet. W would be 0, 0, 0, 0 all the way down, and then we have our constants, which should be 40, 60, 50, 35. And now let's go ahead and put in our W. Remember, when you're setting up the tableau, we have to rewrite the objective function. So it's W minus 45y1 minus 86y2. And so we will have a negative 45 coefficient for y1 and a negative 86 coefficient for y2. Zeros everywhere else except for z. And now we have our initial tableau. Once you have the initial tableau, it's just a matter of applying the simplex method as we have in the past. So what I've done is, in Blackboard, I've attached a PDF that has my work that shows the row operations that I did to apply the simplex method. You should have to pivot twice, so you should go ahead and try that on your own, and you can follow along the work that I included in the PDF. But I'm not going to do it here in the video because then it would take, it'd be another 30-minute video, so I don't want to do that. So check out the PDF that's attached in Blackboard, and you can see the step-by-step work for each of the different pivoting operations that we have to do. So I'm going to go ahead and give us the final tableau now. Alright, so this is our final tableau. I've gone ahead and just written it in for us here. And notice that we know it's the final tableau because there are no negatives in the final row. So we know that we've pivoted as many times as we need to, and we have found the maximum value of the objective function. So now, this allows us to solve our dual problem. Remember, the original problem. This does give us a solution to the dual, but the question that we're really trying to answer is, what is the minimum of the original objective function? And our theorem tells us that the minimum value of the original function and the maximum value of the dual are going to be the same. And so we can determine everything we need to know for the original problem from the final row of our final tableau. So remember, each column of our tableau represents specific variables. We had y1, y2, x1, x2, x3, x4, and then this would be our w, which in this case is the same as our z value, right? And then this number right here is always our actual value for z. So we can interpret our solution from the final row. We can say that z has a minimum value of 86 over 3. So z has a minimum value of 860 over 3. And this is approximately, let's see, 286.67. So we have a minimum value of approximately 286.67, and this is going to occur at the x1, x2, x3, x4 point given by x1, x2, x3, and x4 from the bottom row. So x1 would be 49 over 9, x2 would be 31 over 27, x3 and x4 would both be 0. If you wanted to use decimals, then this would be approximately 5.44, 1.15, and then 0 and 0. And I would take either one. Okay. So to solve for the minimum value of a standard minimum linear programming problem, we have to write the dual problem and then solve that standard maximum. By solving that standard maximum, we have in turn solved the standard minimum that was related to it. Okay? Alright, that's all for now. I'll see you in the next video.